I'm starting to record and go live, but okay, we're talking about the worksheet problems. So we've got two functions. One is f of xy is equal to x squared plus y squared, and the other one is g of xy is equal to x squared minus y squared. And what do we have here? So we've talked about these we've talked about these surfaces enough, but if this is x, y, and z, I think in previous assignments we've already sort of established that this one over here is sort of a excuse me, sort of a, is this a cone or is this a paraboloid? It's a actually, I'm doubting myself. Is this a cone or is this a straight paraboloid? Doesn't really matter. C squared. Or does it behave like this? I don't remember off the top of my head, but this other one is, if I remember correctly, it's a saddle, which is kind of hard to draw, but it kind of looks like that. Yeah. So, excuse me, with this particular one, if I remember correctly, when z is equal to 0, it's just x squared plus y squared is equal to 0. So that's just the single dot at the origin. And when z is equal to positive 1, that's x squared plus y squared is equal to 1, equal to 0. And that looks like just a circle of radius 1. When z is equal to, I believe, 4, x squared plus y squared becomes equal to 2 squared. And that's when it'll achieve radius 2. Radius 2, radius 1, 0. And the z is equal to minus 1, z is equal to minus 4, looks similarly. So I think the idea here is that the radius grows the radius of the circle grows with the square root of z, which means that in choosing between those surfaces I was talking about earlier, you know, a growth of this would actually be too fast, if anything, right? I think, yeah, going off the cuff here, of course, you should all double check, but I think this is essentially saying that z is going to grow faster than the, wait a minute. Do I have this backwards? Yeah, no, I'm sorry. It means, yeah, z is going to grow faster, so it's sort of got a bowl shape like this. Yeah? I think that's right. Yeah, and then to convince yourself, you can look at the other traces. So this should be a 2. To convince oneself, you could also look at the other traces, like for the, for example, the YZ traces, and remind yourself that when like x is equal to 0, that just turns into z is equal to y squared, which looks like a parabola. So yeah, this shape should be convincing at this point, hopefully. I guess I got it mixed up in my head for a brief moment there. But hopefully that should look so good so far. And of course, the idea is that it sort of get rotated around so that each of these sort of obtains kind of like a circular thing, right? So at this point, I think doing traces should be standard fare, hopefully. And for this one over here, the traces from the the XY plane is a little bit nasty, but I think you've done this one before, right? For z is equal to 0, this equation over here just turns into z is equal to x squared minus y squared, which is the same thing as x is equal to plus or minus y, which just looks like a cross through the origin. When z is equal to positive 1, you sort of get that. What do you get? You get 1 is equal to x squared minus y squared. And solving this, you get y is equal to plus or minus the square root of x squared minus 1. Which kind of looks like, all right, it kind of looks like this thing over here, where for x values between positive and negative 1, there is no solution. But outside of it, it kind of looks like a curve that dips up and down. I don't know how to say it. But yeah, as z gets, I believe, larger and larger, this thing over here, you can solve for yourself, it should just sort of move out further and further a bit, right? And for z is equal to -1 and z is equal to -2, it's kind of similar, except for now it's -1 is equal to x squared minus y squared. So that turns into x is equal to plus or minus square root of y squared minus 1, which is going to be very similar to what we have over here, except for it's going to be rotated. So you can kind of see that you have this sort of, you'd call it like a somewhat symmetrical behavior between z going in the positive direction and z going in the negative direction. It's just kind of like a rotated behavior. Right? Hopefully so far so good. But the idea behind this, well, I guess the first question is asking you for a contour plot. And you can sort of think to yourself about how a contour plot is just sort of like a collection of these different, sorry, a collection of these different plots sort of all overlaid in each other. Oh, and remember that for z is equal to negative values over here, I think I misspoke earlier, but these aren't even valid because you can't have a negative value of x squared plus y squared. So for this one, I think you should be pretty reasonable. If you're just sort of overlaying all these circles on top of each other, right, you're just going to get some contour map that looks kind of like this. But one of the questions you need to sort of figure out for yourself is whether or not they're, we sort of established that this growth has kind of a curve to it. So you kind of need to figure out whether that means that the circles are scrunched up close to the origin and getting sort of like wider as you expand. That was not a very good drawing. You need to sort of figure out whether they're scrunched up close and sort of get further out as you go out, or if they are sort of super spaced apart out here, but then end up scrunching together once you get close, once you get out, right? And you need to figure out, you should label each one of these with a value of z, I think. But you should convince yourself, sorry. Yeah, you should remind yourself that if, okay, each of these contour lines is a level curve for z, like this is z is equal to 1, and z is equal to 2, and z is equal to 3, z is equal to 4. You need to kind of like convince yourself whether or not, like, how do you put it? When it comes to like contour maps that you've seen in middle school, right? The really scrunched up curves on a map indicate that it's getting very steep at that point, right? So although you've kind of got the circular pattern down for the first one, you kind of have to also indicate how the steepness is changing. And just judging by this thing, right? The further out you go, the more steep it gets. If, assuming I actually drew this thing correctly, which I think I did, right? As the radius increases by 1, z is going to increase by a lot more than that because of the square relation, right? Yeah. Because remember, this is essentially saying that z is equal to r squared for the radius of the circle. So as the radius increases by 1, z has got to increase by a lot more than that. So with that being in mind, you kind of got to choose between these two pictures, where this one is sort of saying that the scrunchiness is happening near the origin, and it's saying the steepness is near the origin, and it's getting less steep as you go away. Whereas over here, it's kind of poorly drawn, but it's saying that it's not very steep near the origin, but gets steeper as you go away. You kind of got to figure out which one of these makes more sense to you. Sorry, I'm not a very good artist. I'm trying to draw these scrunched together as you get further out, but I'm having a bit of a tough time with it. But anyways, it should be one or the other, and you should definitely make an effort to use scrunched lines to indicate steepness. And as for this one, this is going to be a little harder maybe, but you're kind of superimposing all the stuff we talked about earlier, where you kind of have like positive z going out like this. So these are the lines of positive z, and I think these are the lines of negative z. Shoot. There may also be a steepness consideration, like a scrunchness to... Sorry, you may also have to scrunch the lines together a bit to indicate steepness, but that's kind of hard to represent. But just remember that these are sort of the positive z's, and these are sort of the minus z's, if I remember correctly. And yeah, the contour map is kind of just like superimposing all the, whatchamacallem, superimposing all of the traces together. Okay. So if you're being asked to find a gradient at some particular point, I'm not going to do the math for you. You can go ahead and find the gradient yourself, right? That's just going to be f the partial of with respect to x, partial with respect to y, and I mean, I guess the partial with respect to z, but well, maybe not. Sorry, I don't remember. Is it standard to do the gradient with respect to just 2 or all 3? Maybe just 2. Because I guess we're sort of drawing this on the terms of a... Excuse me, I guess we're drawing this in terms of the 2D map anyways. But yeah, you take the partials with respect to x and y, and then you evaluate it at points 2, 1. Right, so plug in x, y is equal to 2, 1. And I won't calculate it for you, but just kind of looking at the behavior that's gotta, you know, what it's gotta be, right? 2, 1 is gonna be a circle with radius, what is this, like root 5? Right, radius root 5. Which means that the z value is gonna be equal to 5. Okay, so I'm going to maybe draw another z of radius 5. Or, sorry, z is equal to... Sorry, z is not a radius 5. Z is equal to 5, right? And what this is essentially saying is, if you're being asked to draw the gradient at some point, like let's say 2, 1 is like over here, 2, 1, you're being asked to draw the gradient. And remember that you can figure this out basically right away without having to really mess around with precise vector directions, because you can remember that the gradient is sort of the direction of steepest increase. And with circles, that's always going to be, well, it's generally true that the direction of steepest increase is perpendicular to the contour line, right? And that's especially easy to see because we have circles. So the direction of the gradient has just got to be directly outwards. And it's got to be directly outwards rather than directly inwards, because we're talking about the gradient is the direction of steepest increase. And remember that with this particular shape, going the further out you go means the higher you go. So that's justification for that. Okay. And then now it's talking about for the gradient of g at 0, 1, right? Of course, yeah, go through that work yourself to verify, but I'm just giving you the intuition here. Now for delta g at 0, 1, which direction do you expect delta g, 0, 1 to point? So that's basically like right here. Yeah? And remember that these values are negative, so this is z is equal to -1 and z is equal to -2. So just going by what we know about gradients, it's either got to be upwards or downwards, right? Just because it's got to be perpendicular to the level curve, to the contour line. So now you just got to decide for yourself whether it's got to be upwards or downwards, keeping in mind that the gradient has got to be in the direction of positive change, right? Yeah, okay. Yeah, it's got to be in the direction of positive change, so just be really careful about that. And check to make sure that you're pointing your gradients in the direction that z gets larger, more positive. So yeah, you got 2 choices, figure that out for yourself. And okay, now we're finally talking about the second derivative test, right? Second derivative test. Right, so I actually reviewed some notes here, and if I remember correctly, the second derivative test is kind of presented without much motivation. in multivariable calculus. I don't think they really give you a proof of it or anything. But just sort of drawing the analogy to one-dimensional calculus again, if you had some shape that kind of looked like this, right? You would, to look for an extrema, you would sort of first take the tangent line and figure out when that tangent line was equal to 0. And then once you did that, you're not guaranteed that it's a critical point yet because it could be an inflection point. So you sort of had to check, right? And one of the ways you can check is not a guaranteed way, but one of the nice ways that will give you an answer if it works out nicely is a second derivative test, which basically just measures the concavity, right? It measures the concavity here. And if the second derivative is positive, right, that means it's sort of concave upwards. And that's, if it turns out to be positive, that's enough proof that it's concave up. If the second derivative turned out negative for a different curve, right? So if this is y is equal to x squared and this one is y is equal to minus x squared, second derivative would have turned out negative here, which would tell you that it's pointing downwards, right? So if it's pointing downwards, it's got to be a maximum. If it's pointing upwards, it's got to be a minimum, right? So the concavity tells you whether or not it's a maximum or min. And of course, if the inflection point is, if the second derivative is 0, it's sort of inconclusive to where you'd have to investigate further with higher level derivatives, if I remember correctly, or with what do you call it? Maybe it's an inflection point or something like that. So that's the second derivative test in the one-dimensional version. So this is one-dimensional calculus. Now in multivariable calculus, we have the issue is that we have derivatives in multiple directions, right? We have fxx, we have fyy, and we also have the mixed derivatives. So these ones, I forget how to physically interpret these, but these two right here, I kind of like saying, if we look at sort of our, if we sort of look at our paraboloid example, right? I think this is called a paraboloid. This one is basically saying that in the x direction, x, y, and z, it's saying in the sort of what do you put it? And it's sort of saying the slice through the x. How do I put it? Fxx would be positive at 0 here, because it's kind of like saying the parabola, if you take this thing a slice through the xz plane, it looks basically like a parabola, right? And that has an upwards concavity. So this is basically saying that, fxx is positive and fyy will be positive if you go ahead and calculate these things. And it's kind of like saying the two concavities along certain slices are both positive. This one I don't have a great way to physically interpret, unfortunately, but sort of putting this together using the second derivative test, if I remember correctly, turns into fxx, fyy minus fxy squared, right? And these are all going to be evaluated at the point of interest. I think I put the cart before the horse a little bit. Remember, the very first thing you need to do is figure out the critical points where fx is equal to 0 and fy is equal to 0, where the partial derivatives are 0, right? That's kind of like the equivalent of, in this case over here, where you were first finding when the tangent line was equal to 0. Here, it's like finding where the tangent plane is equal to 0. That's the first step of your search in looking for extrema, is figuring out the critical points. Of course, there's no guarantee that it is actually a critical point. You have to tell whether it's a maxima, minima, or saddle point. But that's what the second derivative test here is for. Second derivative test. Well, I guess, yeah, the second derivative test is when you take fxx, fyy, and subtract fxy squared. So again, the intuition here is basically that, all right, for the paraboloid over here, fxx and fyy are both kind of positive, right? And that's kind of like the multi-dimensional analog of this parabola over here, which was sort of like concave upwards in one dimension. Here, it's sort of like saying it's concave upwards in at least 2 dimensions, like the x and y dimension, right? And then if you can altogether show that this sum, I think they call it D, capital D, if they can show that D is greater than 0, you can conclude that it's a minimum, if I remember correctly. Yeah, if it's sorry, if it's greater, excuse me, if this d is greater than 0 and fxx or fyy is greater than 0, this is enough to conclude that it's a minimum, which is kind of what we would expect here, right? Because just looking at it, we would expect this point to be the point with 0 partial derivatives, because it's sort of got the one with a horizontal tangent plane. And we would expect this to be a minimum, so verify that this is exactly what you get with your second derivative test. I'll let you go through the work yourself. Right, just take the mixed partials and put them in this arrangement. They don't really justify why it's this particular arrangement, but hopefully it's reasonably intuitive, at least apart from the mixed partial derivative. The more justified explanation is, I think, slightly higher level math. But okay, so keep in mind that for a... so just going through the other parts of the partial derivative test, second partial derivative test, if d was greater than 0 and fxx or fyy was less than 0, then this would be a maximum, right? And just think about this, kind of hopefully makes sense, right? Because d being d, like, be very careful with the signs here. D is greater than 0 in both the max and the min. It's this sign over here that changes directions. And what this is saying is basically saying that d, the sign is sort of gets dominated by this thing, right? Like these two things multiplied together and get a larger positive number than whatever the magnitude over here is. And that's basically saying that, that's basically, like, how do you put it? D being greater than 0 sort of says that fxx and fyy kind of have the same concavity. And then you got to check the individual concavities themselves to figure out whether they're both positive or both negative, right? D being greater than 0 guarantees that these two things have got to be the same sign, I think. You can maybe check why that is. Maybe think through why that's the case just looking at the signs for this equation, right? If this thing is greater than 0, that guarantees that fxx and fyy have to be the same sign. Gosh, these conversations are always kind of messy. But, all right, so that's the minimum condition and the maximum condition. Let me maybe just draw out the max, right? If you had a very similar paraboloid that was just pointing downwards, right? Maybe the equation looks like minus z, or sorry, maybe it looks like z is equal to minus x squared minus y squared, right? You would expect a lot of similarity, right? The d would be greater than 0 in this case. Go verify that for yourself, right? The tangent line would still be here, and this point would be a maximum. And you would just kind of see that fxx and fyy would both be negative parabolas, right? Like, just sort of think about taking the slice along the x direction and along the y direction, and you would get negative facing parabolas for both. And the idea is that if they're both negative and their concavities kind of agree with each other, well, that means that d ends up being a positive number again. All right. Okay, so that's that. And then we have another case when d is less than 0, right? So if, again, d is the fxx, fyy minus fxy squared. And what this is basically saying is that the mixed partial behavior fxy squared ends up dominating this term. And when this happens, you don't need to check fxx or fyy. You can just immediately conclude that it's a saddle point. So looking at the graph of this thing over here, we've shown before in previous sets that this is more or less a saddle. Remember, it looks like this thing. So you'd really expect to get d is less than 0 when you go through the math. And finally, for posterity's sake, when you get a situation where d is equal to 0, it's inconclusive. You gotta do more involved testing. And that's, I don't know if it's necessarily beyond the scope of this class, but you don't usually get into the weeds with it. Anyways, I hope that makes sense. I feel like this was a little bit messier than usual. But yeah, it's all about the second derivative test today. I hope it's sort of the comparisons to one-dimensional calculus are kind of intuitive. Yeah. Anyways, I think the last thing it asks you to do is mark these points on your contour plots and kind of justify it. And, spoilers, right? But, like, obviously the minimum was going to be right at the center for the paraboloid. Yeah. And you can kind of see that this point is sort of where all the circles sort of shrink to a point. And yeah, I mean, I guess so, right? Like the further you go downhill, you know, you sort of get to this very valley at the center. And at that point, there is no place to go any lower. Whereas over here, we kind of see that like going left or right means increasing in direction z is equal to 1, but going up or down means z is equal to -1. So you kind of got this weird mixed behavior, and that's sort of what a saddle point is. Where some directions means going up. Excuse me. A saddle point is basically saying, how do you put it? It's neither a maximum nor a minimum. All right. Yeah, I think that'll do it for today. Good luck with these.